Okay, in this video we're having a look at situations that involve constant rate of change. Okay, so any function that is linear will have a constant rate of change. Okay, so our linear functions are the ones that have a constant rate of change. Okay, and just a little recap, remember that our rate of change, well firstly that's our gradient, remember that's equal to our rise over our run, and that can be found using the little equation y2 minus y1 over x2 minus x1. And that's demonstrated with this little picture here. So we've got a linear graph here. Okay, we've got our first point, the one that's more on the left is x1, y1. The point that's more on the right is x2, y2. Okay, now it won't matter where these 2 points were on this line, okay? Because the rate of change is the same anywhere on there because it's a constant rate of change. So these 2 points could be anywhere on this straight line and you're still going to get the same value for your rate of change. Okay, we've got a little example here, okay, that we're going to have a look at. We're told that 3 cars are driven along a 2 kilometre straight track. Car X travels at 1 kilometre per minute. Okay, car Y has a speed that is double that of car X, and car Z is half as fast as car X. Okay, what we need to do is illustrate this situation with some distance time graphs. Okay, so what we need to do is we need to set up some axes here. Okay, so this is going to be our distance. Okay, and this is going to be our time. Right, now we know that to do 2 kilometers. Okay, so we'll set this upper limit, okay, to our graph here. Right, now we're actually going to work in meters for this one, so we're going to call this 2,000 meters. Okay, we're also going to look at going in seconds along here. Now we'll get to what our scale needs to be there. Okay, so we need to think about this. Okay, so we go at a rate of, in this time we're going to say is in seconds. Okay, so we know that car X travels 1 kilometre per minute. So it's pretty easy to see that it's going to take 2 minutes, okay, to do our 2 kilometers. So we'll say in here, our 2 minutes is going to be 120 seconds. Okay, we know we're going to start at the starting point. Okay, so we're going to look something like this. Okay, so if we're going to work out, actually we'll get back to working out what our gradient of each of our lines are. So this would be car X. So then our car Y has a speed that is double that of car X. Okay, if the speed's double, it's going to take half the time to complete our 2 kilometre long track. So it's only going to take 60 seconds this time. Okay, for car Y. Car Z, however, takes twice as long. Okay, it's because it's only half as fast as car X. Okay, so it's going to take twice as long, which will take us up here to 240 seconds. Okay, for car Z. Okay, now if we're going to look at our gradients here, okay, we can see for car Z, let's start with that one, as soon as we're here. For car Z, we have a rise of 2,000 meters over a run of 240 seconds. Okay, or it's our rate of change is 2,000 over 240, which can be simplified to 8 1/3. Okay, for our rate of change. Okay, which is really that's 8 1/3 meters per second. Right, if we have a look at X this time, okay, well X we do that 2,000 over a time of 120 seconds, which means our rate of change is 16. Okay, and 2/3 meters per second. Okay, just want to simplify that fraction. Okay, and when we look at car Y, well, our rise is still our 2,000, but our run is only 60. So we're 2,000 on 60, which gives us a rate of change of 33 1/3 meters per second. Okay, so these are the type of questions we're going to be looking at. Okay, they're all going to be linear. Okay, we're all going to need to look at our rate of change in the same way that we think about our gradient. So we just need to get into that thinking that our gradient is representing our rate of change. So whenever we're looking at our rate of change, we need to be thinking, oh, okay, I'm looking at my gradient. Okay, so hopefully that's enough to get you through this section.